Welcome. Our topic now is gravity and satellites. So while we're working on this, I'm going to play some visuals from the International Space Station of the Earth. Okay, so I thought that was kind of cool. All right, so I've recorded a few interesting values that we might use later on. Got the International Space Station orbital height, the mass of the Earth, and the radius of the Earth, which we need for later on. Okay. Alright, so let's start off with a few things that we're going to need as well, a few equations we'll need. Okay, we've got Newton's equation of universal gravitation. So if you haven't seen this before, each body in space is attracted to each other mass in space, the masses. Every mass in space is attracted to every other mass in space with a force that's proportional to the product of the masses, that's that one, and inversely proportional to the distance between them. Between two masses, you can come up with an equation as such. The equation we're going to use. Alright, now for most of this, we're going to have a planetary mass that we just call capital M. And we're going to have another mass which is little m. And for a lot of this stuff that we're going to do to work, big M has to be much larger than little m. By orders of magnitude, that's why we use the double greater than symbol. Okay, now for satellites, we're going to use the centrifugal force formula. Okay, and so we're only looking at a small group of orbits, particularly orbits that are uniform circular motion orbits, such that they have uniform speed, they have a circular orbit. Now, for gravity to work with this, the center of the orbit must coincide with the center of mass of the planet. Okay, and the only force providing this circular orbit is gravity. Alright, so let's do some derivations first. First of all, I'm going to do derivation of gravitational acceleration. Okay. Better. There we go. Okay, so G. Okay. All right. So the force providing this. So imagine we've got planetary body. So use our example up here. A planetary body, m, and little mass, little m. Okay. And this works on the surface of the Earth too, and that's where we're going to actually do the example. But in general, you can work out the acceleration on the little mass by the following formula that we will derive. Okay. Now the force acting on mass m, little mass m, little m, okay, is F equals G times big mass, little mass over r squared. Okay. Then acceleration of m, A equals, now remember that A is equal to F divided by the mass accelerating, so that's in the second law. A equals G m little m on r squared divided by little mass. So we can cancel out those two. Now you notice that this is independent of the little mass. So we're going to say G equals A equals Gm on r squared. Okay. Sorry. That. Good. All right, so we got that. Now, So let's calculate that near the surface of the Earth. Yeah. Let's just start a new page for this. All right. So G equals that's better. All right. 6.673 times 10 to the minus 11, that's a value for big G, times by the mass of the Earth, 5.977 times 10 to the 24, divided by the radius of the Earth. Now, that will be 6.371 times 10 to the 6, square that. Okay, so let's put that in the calculator and see what happens. Okay. 6.673 E minus 11 7. There we go. Times by 5.977 E24 divided by 6.371 or 6 squared. Okay, and we get approximately 9.83 meters per second squared. Okay, which would round to, through our two some figures, 9.8. And as you're aware, then on our Earth, the radius where you stand from the center is different. That the Earth is an oblique spheroid, wider at the equator than it is at the poles, and also you have Earth is not completely uni-leveled, even so. Okay. But you could work out the acceleration of any body essentially near another like large planetary body by using this. Now the argument that we're making is that the bodies accelerate towards the Earth, and the Earth does not accelerate towards the smaller bodies. They have the same force that is given by Newton's third law, which complies with the Newton's law of universal gravitation. They're both attracted by the same force. Now because the Earth is very much more massive than the bodies that we're talking about here, then the Earth does not accelerate towards the little mass accelerates towards the Earth. The Earth's acceleration is unmeasurable. Okay, so that's an example of the little g calculation to get you 9.8. You can do this for any planetary body, just put in the values, so put the mass of the planet and the radius, and you can come up with that. Okay, so let's also, now let's actually look for satellites. So for satellite motion, uniform circle. We're taking the uniform circle example, so we can't have elliptical orbits. We can't have other weird stuff like Lagrangian points and things like that. So we're just talking about a single body in orbit around a planet, usually very small, such that the planet doesn't move as a result of the small body that's orbiting it. Okay, so gravity, force of gravity equals the centrifugal force that's providing it. So we got G m little m on r squared equals mv squared on r. That's your centrifugal force. So we can cancel the little m's. All right, let's tie this together. And also while we're at it, so we're timesing by r and we're dividing by m on both sides. Okay, so times that r across, and I'll swap the sides as well. V squared equals G capital M on R. Now you can, what you could do with that is write it as V equals square root of gm on r as such. Okay, so that's our first major equation in regards to the satellite motion. Speed of the satellite is equal to the square root of gm over the radius of the orbit. So they're tied together. For this sort of motion to happen, these two variables are tied together in relationship, so you can work out one from the other. I should also write down, I'll need it in a moment, the period formula. This is for all kind of circular or basically it's okay. Period is equal to circumference of your circle divided by the speed. So really, it's just time equals distance on speed. That's all it is. Just be careful with this because v and r are tied together. So you can't exactly fix v, change r to solve for t. It's not going to work because we're talking about a particular case. It will work for a number of other situations where this is true, like whenever you're moving in a circle, but it will not work for satellites. Okay, but we are going to use this. I'm actually going to come up with another derivation. But before that, we'll just do an exercise. Let's have a look at the International Space Station. All right, so I've got the radius of it, so I'm going to look at the speed. I've edited my mistake out, and I'm going to redo this. Okay. So, h equals 400 kilometers, which is 4.00 times 10 to the 5. Now, r is equal to height. Now, height is just the distance above the ground. So if I was to look at my diagram, just be looking at the height. Let it focus. The height is that, not the radius, that's height there. Okay. So height plus radius of Earth. Okay, and radius of the Earth. So we've got 4.00 times 10 to the 5 plus 6.371 times 10 to the 6 meters. Okay. So let's work out what that is first, and then we can actually put it into the equation. 4.00 E5 plus 6.371 E6. Okay, so that's actually the radius there. That's the radius. 6.771 times 10 to the 6. That's better. Okay. Now let's work out the speed now. V is equal to 6.673 times 10 to the minus 11 times 5.977 times 10 to the 24 divided by our radius, which is 6.771 times 10 to the 6. Okay. Go. Go. Okay. Let's do the calculation of that. All right. There we go. All right, so the speed is 7,650 meters per second. Okay. All right, now let's have a look at that, because I did see tabulated data, and yes, that's correct. Well, about 7.66 kilometers per second is what they say over here. Okay, so about in the right ballpark. Now, it's not completely consistent orbit, not completely circular. It does actually make mention of that in read up on the ISS, but it's a decent enough approximation for our purposes. All right. So that was a calculation, an easy calculation of speed from that formula. All right, so we're going to do another derivation. So this is the one that's actually going to tie together radius and period. So what we're going to need, we'll start off with our equation. So we've got the one we had before was v squared equals gm on r. So that's when we cancelled out the little mass. All right, the other equation we're going to need is v equals 2 pi r on period. Okay, so that's a rearrangement of what I wrote earlier. I'm actually going to take that one and square it. So I'm actually going to write that as v squared equals 4 pi squared r squared on t squared. Okay, now what I can do is essentially I can equate, this is the formula that ties together orbital speed with radius. That came out of the equating universal gravitation with the centrifugal force formula. Okay, now this is just any object moving in a circle. So you got like this. It's just speed equals distance on time. So distance happens to be circumference because it's moving in a circle. And as it's moving in a circle, that's a period. It's t. Okay. So if we equate these two parts, we'll have g m on r equals 4 pi squared r squared on t squared. Okay, so we've got that. All right, so to that I'm going to multiply both sides by r and multiply both sides by t squared. So just move a few things around. So t squared comes across, t squared gm equals 4 pi squared r cubed. Okay, then divide over g and m. Okay, divide g and m. We'll have t squared equals 4 pi squared r cubed over gm. Okay, so you can work out the period in terms of the radial orbit. Now you can also work this out the other way around. You can work out radius from period. That's useful, so I'll just take that formula for now. You can take the square root and write it in that form if you wish. But that's just one form of that period formula. Remove everything around. R cubed equals gm period squared on 4 pi squared. Now, that formula is actually quite useful because we're going to look at geostationary satellites. And we're going to actually do the calculation for that. Okay, so geostationary, they are always over the same point of the Earth. Now this can only happen at the equator because it has to follow the Earth as it rotates. And you can't do that and maintain one of the conditions we mentioned earlier, that being the center of the orbit must coincide with the center of mass of the planet. You can only do that if you're traveling with the Earth and following the equator. And so you're essentially always above a point in the equator. All right. So, but to make that happen, your period must be 24 hours. Okay. All right. So for that, we can work out the radial distance, and I think I will work out the height above the ground as well. Okay. So r cubed equals 6.673 times 10 to the minus 11 times 5.977 times 10 to the 24 times by, okay, now I probably should have converted this to begin with, but 24 times, so 24 hours, one day, 24 hours times 60 equals, work that out. Okay, 86,400 seconds. I need that in seconds. 86,400 squared. Alright, divided by 4 pi squared. Alright, now let's take a look at that. What was the calculation we're going to get? Alright, 6.673 e minus 11 times 5.977 e24 times my last answer, which is the time in seconds, squared, divided by 4 pi squared. There we go. Okay. Alright, that looks big, but remember that's still cubed. So we need to take the cube root of that. But I'll write it down for now. Alright, and r equals the cube root of that. Alright, so let's approximate that. Alright, the cube root is there. Oops. There we go. Cube root, my last answer. That looks about right from memory. 4.225 times 10 to the 7. So it's like, it's okay, that is, if it was in kilometers, that would be 42,250 kilometers above the Earth. Okay, so that's 10 to the 7. You notice that's much higher than the International Space Station. I think it's actually quite high above the Earth, the geostationary point. It's the only, I mean, you've got a circle of positions that you can place a satellite into. It always has to follow the equator, always go in the same direction as the Earth for this to work. Okay, let's work out the height. So the height is, or altitude, height is a radius take the radius of the Earth. So we're talking about the height above the surface of the Earth. Alright, so subtract that. Okay, we've kind of done this backwards already, but just one more time. 6.371 E6. Okay, so height above the Earth, 3.588 meters. Times 10 to the 7 meters above the ground. Okay, so that's where you find the geostationary satellite. It'll be that high above the ground, and that has consequences in terms of some of the what you might use the satellite for. Okay, but those are the major derivations for this chapter. So we've done them all. We've got the period formula, which was the last one we did. Okay, going back over them again, you've got the gravitational acceleration formula, which you probably would have seen in the Year 11 course, I hope. And also we've got the, over the other page here, we've got the relationship between speed and radius that we got from equating universal gravitation with centrifugal force. So there's all your equations, guys. I hope you learned something from this or helped revise. So, yeah, have a good day and keep watching the sky.